evolving. As continents shift and clash, volcanoes erupt, and glaciers grow and recede, the Earth's crust is carved in countless fascinating ways, leaving a trail of geological mysteries behind. And one of the greatest is right here, at Yellowstone National Park in Wyoming. This is one of the world's most geologically active places, shaken by up to 5,000 earthquakes every year, and with more geysers and hot springs than in the rest of the world combined. Why is Yellowstone so active? How did it form? And why here, in the heart of the Rockies? Scientists studying Yellowstone are uncovering a violent past, carved by water, crushed by ancient glaciers, and blasted by the biggest volcanic eruptions ever known on the planet. And even today, Yellowstone is one of the most dangerous places on Earth. Yellowstone National Park is one of the most amazing places on Earth, and it's unique. It contains some of America's most stunning scenery and wildlife that attracts 3 million tourists a year. To understand where Yellowstone came from and why it is so active today, we need to take a journey back into the distant past of the North American continent and deep into the Earth's interior. Yellowstone sits 8,000 feet up on a remote mountain plateau, primarily within Wyoming, but stretching into parts of Idaho and Montana. The park covers 3,468 square miles, 63 miles north to south, and 54 miles east to west. And it's on top of one of the world's most unusual and deadliest geological structures.
What's unusual about the park? Are the wildlife unusual? No. Is the wide open space unusual? No. You've got it all over the western U.S. What's unusual? It's a very unusual geology that created the park. Yellowstone was founded as the world's first national park because of the geology.
It's this strange geology that attracts teams of scientists to the park. Their task? To piece together the story of the incredible processes that built this unique, extraordinary landscape by digging deep into Yellowstone's past.
The geologic history of Yellowstone goes back to the formation of the North American continent. Some of the rocks in Yellowstone are 2.8 to 3.2 billion year old rocks, some of the oldest in North America.
Only by traveling back into the past can we figure out why, in this particular location, there are 2,400 miles of rivers, more than 300 waterfalls, and the world's greatest concentration of 10,000 hot water springs, bubbling mud holes, gas vents, and geysers. What do these features reveal about this landscape and how it was formed? The investigation begins at Yellowstone's star attraction, Old Faithful. It's a key clue to what's going on underneath the surface. Located in the southwest of Yellowstone Park, the geyser puts on an explosive display every 90 minutes or so, blasting out thousands of gallons of scalding hot water.
Yellowstone is like no other place on Earth. There is so much heat coming out here. It's really a singular phenomenon. Well, after about a 90-minute nap, Old Faithful has roared back to life. It wasn't actually napping, it was recharging. The temperature of the water was increasing, the system was pressurizing.
Morgan has chemically dated the rocks and discovered that 3,000 years ago, the boulder was blasted out of the ground by the hot water explosion of a gigantic geyser.
You would see boiling water, rock fragments, and fine muddy material being ejected up into the air as high as 3,000 to 5,000 feet. And then at some point, material would start raining down from this explosion column. Now, you wouldn't want to be standing next to one of those.
Indian Ponds is the crater that the geyser left behind. But it is dwarfed by the crater Morgan has found at Mary Bay in Yellowstone Lake. Morgan has dated this geyser explosion to 13,000 years ago.
So here we are in the middle of Yellowstone Lake, and it's, as you can see, a beautiful day, and it's nice and placid. But on the floor of Yellowstone Lake, it's anything but quiet.
Morgan's research proves that geysers were exploding around the lake and even under the water between 13,000 and 3,000 years ago. And their size suggests that whatever was powering them was huge. But is it still active today? A clue comes from underwater vents at the bottom of the geyser crater. They pump out vast quantities of hot water and gases. To find out what's creating the gases, Jake Lowenstern and his assistant collect samples from the hot springs in the center of the park. The funnel they use is designed to collect up gas bubbles before they reach the surface, so that they're not contaminated by ordinary air.
So let it sit for 5 minutes, let the oxygen get out.
Yeah. It is a very complex mix of gases, but we have a lot of tools that we can use to try to unravel this rather complicated information. So we'll look at all of the gases that are coming out. We can learn about the different kinds of rocks beneath Yellowstone and try to understand how things might be changing from week to week or year to year or decade to decade.
Analysis of the gases reveals that they are a mix of carbon dioxide, sulfur dioxide, and hydrogen sulfide. It is the same mix that is found coming out of volcanoes. But the final clue to what's actually going on underground is found on the edge of the same hot springs.
So these are quartz crystals that we collected on the side of the pool there. This stuff is what remains. It gets tossed up. It forms a little berm around the side of the pool. It's all beautiful little quartz crystals. Some of them have a little bit of iron staining and other things. But most of them are nice shades of yellow and clear.
Quartz crystals like these can only have formed as a hot, molten rock lava flow slowly cooled after being erupted onto the surface from deep underground. So the crystals are clear evidence that under the springs is a volcano. Yellowstone's hot water features all point to one conclusion. Yellowstone must be powered by the heat of a volcano. Geysers only erupt if the rocks are hot enough to turn water into steam. Gases from underwater have the same composition as those from volcanoes. Quartz in the hot springs must have come from volcanic lava.
There's an immense amount of energy coming out of the ground that's expressed by the geysers, the mud pots, the hot springs, and the steam vents. Where's all that heat coming from? It's coming from the molten rock associated with the Yellowstone volcano.
But that leaves a big question unanswered. In this gentle rolling landscape, where's the volcano? Yellowstone's unique volcanic geology is potentially deadly dangerous. It makes it crucial to monitor what's happening under the ground.
The Yellowstone volcano is a very, very active volcanic system, and so it really requires observation. Everything that we do here has a research component, but it also has a volcano monitoring component. And if activity picks up here, we're going to want to know something about the plumbing system beneath us here.
To try and predict when Yellowstone's hidden volcano will erupt in the future, scientists study its geological past.
Part of our task is to look at the landscape and read the geologic story. And there's so many clues and so much evidence here to look at that it's a fascinating place to work.
Scientists began investigating Yellowstone even before it became the world's first national park in 1872. But observations of this astonishing land began long before that. Dating ancient arrowheads shows that Native Americans first lived here 11,000 years ago. Their legends of Yellowstone's angry spirits who made the ground tremble were passed on to early explorers such as Lewis and Clark. Later reports from trappers, explorers, and mountain men like John Coulter and Jim Bridger told of geysers that fired 70 feet into the air and springs so hot that meat was readily cooked in them. But these were thought to be tall tales until the 1860s, when geologists investigated and found that the lava flows and hot vents were signs of volcanic activity. But something clearly wasn't right. Nobody could actually find the Yellowstone volcano.
We say that Yellowstone is one of the world's most active volcanoes. People come out here, visitors, other scientists, and they say, "What do you mean? I don't see a smoking volcano. I don't see a big, steep volcanic crater. All the things that one normally thinks of for an active volcano."
So without obvious signs of a volcano, scientists hunted for other clues. They would find them in the sweeping forests of lodgepole pines. These are the only plants that thrive on the poor soil that comes from a particular type of lava called rhyolite. And Yellowstone's constant plagues of mosquitoes also reveal the presence of that same rhyolite lava.
The rhyolites are not very permeable. And so it creates these little ponds of water that never go away. And those are a wonderful breeding ground for mosquitoes. There are a lot of mosquitoes, if you can't see them, flying around my head.
So the pine trees and the insects both indicate that there's a lot of rhyolite in Yellowstone. And that's important, because rhyolite lava creates incredibly violent volcanic eruptions.
It's much more like a bread dough. It's about 1,000 to 1,000,000 times thicker or more viscous. We put a bunch of gas in it, we can have a very explosive eruption.
But if rhyolite lava is that explosive, how big a bang did it produce? To find that out, scientists looked not inside Yellowstone Park, but in a faraway river valley at Meadow Creek, Wyoming. Cutting down through the land over millions of years, the river has exposed an unusual thin layer of black rock in the cliff face. A nearby road cutting lets investigators examine the mysterious dark rock.
If you look at this sample in detail up close, you can see that here's a pumice fragment,
These red fragments here are little rock fragments, and if we were to make a thin section of this rock and look at it under the microscope, you would in fact see compressed glass shards.
The black layer that geologists call obsidian is actually a type of glass. It's crucial evidence that the rocks and soil here came out of a volcano. Because obsidian is forged when boiling hot ash and gas rapidly cool under great pressure. And that's just what happens when hot volcanic clouds roll out across the landscape. The obsidian forms in the very bottom layers, cooled from below and crushed by the weight of hot debris on top. The ash layer that crushed the obsidian at Meadow Creek is still visible today.
Its base is characterized by this very thick, dense obsidian as the flow came to rest and was compacted. And then above this dense glass layer it grades upwards into a tan sort of region and continues up for about an additional 30 feet. And then up on top of that, as it's exposed today, a modern soil has formed, and we can see growing up there various sorts of vegetation, trees and grasses and things of that sort.
Studying the mineral composition of the ash proved that it came from an ancient volcanic blast in Yellowstone Park. And there's only one way that so much ash could have been blasted so very far away from its source. The eruption must have been larger, far larger than anything ever seen by man. So big that scientists now label it as a super eruption.
We're looking at this deposit from a super eruption, and yet we're over 50 miles from the source of the eruption.
The geologists have recreated what must have happened here on the day that Yellowstone exploded. Incandescent avalanches of ash raced out of the park in all directions.
So this is traveling at very high velocity, easily over 100 miles per hour across the land surface, and obliterating everything in its path.
It was extremely hot when it arrived here, and perhaps as hot as 1,500 degrees Fahrenheit. Twice a pizza oven. I mean, it's just very hot.
So what would it have been like to be standing on this spot hundreds of thousands of years ago? On the day when the Yellowstone ash cloud roared over the horizon.
The impact of this would be absolutely unimaginable. It would be, I think you would be disarticulated, burned, and unrecognizable, and it would be very difficult to find any of you.
All of the evidence about the size of the super eruption helped solve the mystery of the missing volcano. Scientists realized that the super eruption was so enormous that it must have blown the volcano to pieces. Swarms of mosquitoes show that explosive rhyolite lava underlies parts of the park. Obsidian glass 60 miles away reveals that ash flows spread for miles around Yellowstone. And thick layers of debris confirmed how gigantic an explosion this must have been. The problem now is the explosive legacy that the supervolcano left behind. Because a deadly danger still lurks here, hidden deep under the ground. For nearly a century after Yellowstone National Park was established, nobody realized one astonishing fact. That the park is located inside one of the biggest volcano craters on Earth. It wasn't until the late 1960s that American geophysicist Robert Christensen realized that rock formations he had been studying for several years all around the edges of the park in fact formed a giant circular ridge. He compared his findings on the ground with a series of NASA pictures taken between 1966 and 1970, confirming that the ring was the rim of a giant crater 45 miles across. Parts of the crater rim are still clearly visible today, but the other edge is almost out of sight. Finding the crater coincided with another scientific discovery in a totally different part of the country. In California, scientists identified a strange thin layer of ash buried underneath the modern-day soil. The ash matched material from the Yellowstone crater. Dating the soil layers proved that the ash arrived 640,000 years ago. Scientists at last had a date for the Yellowstone supereruption. Ash was later found all over the western U.S., confirming the huge size of the eruption. At least 80 times the size of the 1883 explosion that destroyed the island of Krakatoa. And 2,500 times bigger than the 1980 eruption of Mount St. Helens. The almost unimaginable size of the Yellowstone blast means that scientists now call it a supervolcano. But that creates another mystery. In this peaceful landscape, where is the steaming hot crater that the volcano must have left behind?
Today, when you're looking out across the landscape, you see rolling hills and trees. So obviously there's not a big hole left in the ground from the eruption of the Yellowstone volcano. So something else has happened. One of the first processes was infilling with all sorts of volcanic lava flows. And if you look just down from the landscape toward those trees, you'll see one of the oldest lava flows that happened after the 640,000-year eruption.
Over hundreds of thousands of years, this flow has weathered into soil and been covered with trees. But elsewhere in the park are a different type of lava deposit, still bare of vegetation, because this lava was still erupting up until about 100,000 years ago. The later lava was far less explosive and more runny, and cooled slowly. It smoothed the harsh volcanic landscape into Yellowstone's softer countryside. That made Yellowstone at first more tranquil. But there's evidence here that the land was soon buried once again, this time by freezing snow and ice. The ice that polished the rocks has a story to tell. It offers crucial evidence about volcanic forces still shaping the park to this day. Its tale unfolds through the tiniest of clues. Scratches on the rocks reveal which way the ice was moving. They show the glaciers always slid the same way, outwards and downwards from an ice cap at the heart of the park. The only conclusion is that something pushed up Yellowstone Park so much higher than the surrounding hills that glaciers formed on the top. What force could possibly be powerful enough to have raised Yellowstone's peaks up into the air? The first clue to help answer that question comes from Yellowstone's numerous earthquakes.
When the ground deforms, it creaks and groans like a Stradivarius violin, and the creaks and groans are essentially earthquakes.
The quakes are recorded by seismometers all over the park.
The earthquake monitoring is a critical part of the picture because it's the stethoscope that we have to really see and sense the heartbeat of the system.
Smith is investigating a puzzling geological mystery. Yellowstone has up to 5,000 earthquakes a year, even though it's in the stable heart of the North American continent. Scientists needed to know what was happening underground to shake the park so much. To find out, they plotted the precise locations and depths of earthquakes under the ground. So why are there so many quakes? The answer had to wait until the mid-1980s, when ever more powerful computers first let scientists see into the Earth. Seismic waves spreading out from earthquakes travel rapidly through cold rock, but slow down when the rocks are hot. The varying wave speeds can be translated by computers into color 3D images, revealing exactly where hot rock lies under the ground.
Seismic waves propagate through the earth, just like X-rays go through a body. So we use the same physics to reconstruct the structure of the earth beneath us.
The seismic waves have outlined the park's underground structures, revealing a graphic history of what's happened under Yellowstone. They reveal this gigantic reservoir of molten rock which created Yellowstone's crater when lava erupted out, and the ground above collapsed into the space left behind. And the seismic waves still slow down under Yellowstone today, showing that the magma chamber still lurks under the park. It's more than 30 miles long, 25 miles wide, and 10 miles in depth. But its size alters from year to year as it fills or empties with semi-liquid rock at an incredible 1,500 degrees Fahrenheit. This is the hidden beating heart of Yellowstone Park. The way it moves deforms the ground above, explaining the fault lines and the earthquakes they produce. And its heat ultimately powers all of Yellowstone's hot water pools and geysers. Subterranean Yellowstone is giving up its secrets. Seismographs record thousands of earthquakes in the park. And the evidence of earthquake waves reveals a massive magma chamber miles under Yellowstone's surface. But the Yellowstone investigation is far from finished. Because there's evidence of another, even more monstrous-sized structure under the park. By the beginning of the 21st century, scientists investigating how Yellowstone was made had images of what lay under the park. But there was a problem. Technology only allowed a view of a few miles below the surface. Then, as more and more data was fed into more and more powerful computers, there was a breakthrough. In April 2006, geologists published new diagrams of hot structures far deeper under the park, and computers painted more detailed pictures. The results were startling. Investigators saw for the first time the sleeping monster that lies below Yellowstone Park. Snaking down hundreds of miles into the earth, far deeper than the relatively shallow magma chamber, is a colossal volcanic pipe. Nobody's certain how deep it goes, but they can picture it down to 400 miles or more, twice the distance between Washington and New York. Smith makes an educated guess about what the underground plume is like.
Our best estimates now, as they start doing the physics and the dynamics of these things, it's like a conduit of melted rock, like a chimney.
That chimney, called a hotspot, pumped up enough heat to melt the rocks of the crust and fill the overlying magma chamber, which then erupted to blast out Yellowstone's vast crater. Understanding how the crater formed was an important moment for the investigation, because there was evidence that similar eruptions had happened before, many times before. Throughout the 1960s, various teams of geologists studied the Snake River Plain to the southwest of Yellowstone Park and found traces of ancient volcanic craters. The crater rims had long been eroded, but their outlines were confirmed by aerial pictures over the following decade. They ran in a straight line along the plain, heading for the heart of Yellowstone Park. On average, each crater was a couple of million years older than its neighbor. Investigators realized that these are the remnants of earlier supervolcano explosions, an unbroken chain stretching far back into geological history. It seemed clear that time after time, the hotspot had blasted out a super eruption and then moved on. The hotspot appeared to have traveled hundreds of miles. But that posed yet another riddle. How could a hotspot, anchored to the core of the planet, be moving? An important clue had been found in 1985 by American volcanologist William Scott. He realized that plotting the location of 30,000 earthquakes around Yellowstone produced an amazing pattern. The quakes traced out a giant V-shape on the surface of the Earth. The V-shape wrapped around the hotspot's location. It seemed at first to confirm that the hotspot was still moving, rippling up the land around it with fault lines and tens of thousands of earthquakes. But the real answer lay with the theory of plate tectonics. It showed that it's the American continent, not the hotspot, that's moving. And the chain of craters on Snake River Plain is there because for millions of years, the moving American continent has continually pushed new land over the stationary hotspot.
But as the North American plate moved across this source of heat, it pops through the lid and creates the hotspot track. That's the Snake River Plain. Yellowstone is just the active component today.
The repeated hotspot explosions on land have made Yellowstone unique. Other hotspots have been identified around the world, like the one that has created the island chain of Hawaii. But Yellowstone is the only place where a hotspot has erupted in the middle of a continent. Each of the earlier explosions blew the original mountains to pieces. Then the land smoothed over with later flows of more runny lava that was released from deep under the Earth's crust. Multiple strands of evidence combined to reveal Yellowstone's slumbering monster, the gigantic hotspot plume lying under the park. Earthquake maps show the hotspot's location. Seismic waves reveal the depth of the plume. And earlier craters prove regular super eruptions over millions of years. All of which leads to the most frightening question of all. When will Yellowstone erupt again? Measuring the amount and geographical spread of ashfall from Yellowstone super eruptions produced some terrifying figures. 640,000 years ago, the eruption poured out around 240 cubic miles of material. Enough to bury the whole of New York State tens of feet deep in ash. If it happens again, thousands will die. Vast areas of the United States will be buried in volcanic debris. But when will Yellowstone erupt again? One clue to when that next eruption will happen comes from investigating the eruptions of the past. The hotspot punches out a super eruption on average every 600,000 years. And the last one was 640,000 years ago. But geologists expect that there will be warning signs before Yellowstone explodes again. Volcanic eruptions are usually preceded by an increasing number of earthquakes. The quakes are a sign that underground volcanic chambers are filling with molten rock and expanding to stretch and deform the land up above. Yellowstone Park usually experiences an average of 12 tiny earthquake tremors every day. Most are too weak to be felt by tourists and register only on the most sensitive seismometers. But in early 2009, more than 4 times as many quakes started striking every day. Over one 10-day period, there were more than 500 quakes, some of them up to magnitude 3.9. Powerful enough to frighten the visitors and put the scientists on alert. There's a second indicator of increasing volcanic activity. If more molten rock does inflate the underground chamber, the ground above will rise. And that too seems to be happening right now. Unusual evidence to prove it comes from an unlikely source, the waters of Yellowstone Lake. Around 100 years ago, small steamships carried tourists on sightseeing trips across the lake. But one of the ships caught fire and sank forever below the surface of the lake. But now, Yellowstone's astonishing geological forces have resurrected the ship's remains from their watery grave.
Here we have a boat which burnt down to water level. And so this tells us something about the deformation of Yellowstone. And basically what's happened is that the floor of the lake has risen, bringing the boat out of water.
The reappearance of the wreck shows that land under and around the lake is rising because of the expansion of the magma chamber. Even more alarming, the rate at which it's rising seems to be increasing. In geological terms, a huge area of Yellowstone Park is positively soaring up into the air faster than it's ever done before. The biggest uplift of all has been recorded just a few miles from the shore of the lake. There's a GPS system here, a much more sophisticated version of the one in your car. It measures not only its surface position, but also its exact altitude to within fractions of an inch.
There's a small radio antenna about the size of your thumb that sits on top of this steel rod. And it's anchored in about 3 or 4 feet. So if the ground moves up and down, the antenna moves up and down.
The GPS and the land on which it's anchored are moving upwards.
We're above the magma chamber, and beginning in late 2006, this whole area of ground started to rise at the order of 2 to 3 inches per year. And as of today, this whole system right here has risen about that much. and it's still moving today. And so we're measuring and keeping close track of the deformation, of the uplift that we're seeing at this station.
But does the uplift mean that Yellowstone's supervolcano is threatening to erupt once again?
The question of what lies in Yellowstone's geologic future is fascinating. And I and all of my colleagues would love to know the answer to that question.
The scientists keep a careful watch on the volcano's activity.
The idea of science is to understand the process. And so we have a responsibility to see how this system is deforming and how it's working. And we have to be aware there's still a possibility of volcanic eruptions or earthquakes. After all, that's what made this system. And there's no reason to think that volcanism has stopped.
The Yellowstone investigation has shown that the park